Assalamualaikum. My name is HAZRIQ HAKIM bin JULAILI, and today me and my group will undergo this experiment that we call linear conduction. So this is the apparatus. So the first step, what I want to do is open the water supply. And second thing is check on the material. So the material we use today is brass. For the first experiment we use the brass. And right after we install the material for this experiment, turn on the main power. And then next is turn on the heater. And then open the water supply valve. Make sure the water supply valve is fully open. And for the initial power, we tune to 30 watt. So wait for 5 minutes to take the temperature reading. Alright, after we done record the temperature after 5 minutes, now we tune the power to 50 watt and wait for another 5 minutes. Alright, right after we record the temperature for 50 watt, now we turn the power to 90 watt and then wait another 5 minutes and record all the data. Alright, now after 5 minutes, this is the data for the 90 watt. And right after we record the data, we can turn off the heater and then turn off the water supply and then turn off the main power. And then turn off the water source.
After this, we will repeat the experiment with different materials, aluminum, stainless steel, and copper. So we will change the material with copper to copper. Now, so we will show you what to open this.
Aku buat dia orang makan apa? Mami, dia orang makan grilled cheese sandwich.
Balik ke mana? Balik ke mana? Memang macam ni ke? Memang ada gap kan?
Tutup boleh kan? Tutup lock.
So we will connect the T4 wire to the board.
A very good day, sir. My name is HARISHWAR MOHAN from BMMH3553. Today I am going to explain about linear heat conduction lab report. So here our report for brass. Then we supplied different kind of power in watt, which is 30, 50. Sorry, different kind of different value of power. It is 30, 50, and 90. So for 30, this is our recorded temperature from T1 to T7. Then goes on for 50 and also 90. Then this is the distance from T1 in meter: 0, 0.02, 0.04, and 0.06, and also 0.08, 0.10, and finally 0.12. So this is for brass. Then for next one is stainless steel. The material selection was stainless steel. Same goes to this. We supplied different power in 30, 50, and 90. Also we recorded the temperature from T1 to T7 in Kelvin. Then this one for stainless copper with material 3 with ambient temperature 25 degrees Celsius. Same goes as well. We supplied different power 30, 50, and 90, and also we recorded the temperature. The distance for three materials are same. Then this is for brass. The graph, the line in blue is 30 watt, for 50 is in gray, and red is in 90 watt. So that for this one for stainless steel, the graph is about temperature in Kelvin against distance meter in meter. This is the graph for stainless steel, and also stainless copper. Then the first discussion will be calculate the gradient of the charts. What does this gradient represent in the conduction equation? So the first graph represents 30 watt, temperature K against temperature in Kelvin against meter. So we calculate the Y, which is gradient. Y equals to negative 4.8839 x plus 339.33. So second one will be for 50 watt power. We calculate the Y also. Y equals to negative 3.6929 x plus 327.17. Then finally discussion, the power will be 90. For 90, the gradient will be Y equals to negative 3.3036 x plus 324.1. So as a theoretical, the temperature gradient is the rate of change of temperature with respect to the displacement, as well as the heat conduction happens in the direction of decreasing temperature. When temperature decreases by increasing distance, the temperature gradient becomes negative. Fourier's law defines that the negative gradient temperature and the time rate of heat transfer is proportional to the area at right angles of the gradient through which the heat flows. Then finally, the rate of heat transfer through a plane layer is proportional to the temperature gradient across the layer and heat transfer area. That's all from me, sir. Thank you.
Good day. My name is HARISHWAR SMAIL, and I will be presenting for the discussion for the lab linear conduction for our group. As you can see from this slide, for this question, use the two voltage reading T1 and T7, the given distance between them and the heater power, and the bar area between with equation 5 to calculate the thermal conductivity of the metal bar. Compare it with the typical value given in table 1 explain the cause of error of any error for the different value in the critical and experimental thermal conductivity. And then we proceed to the answer on the next slide. Now, as you can see on this slide, the calculation for the thermal conductivity of A for the brass and the stainless copper. For the brass, for each data, we take the T1 and T2, that is 343.2 kilo per Kelvin. For the T2, 306 Kelvin. The length is 0.12 meter, diameter is 0.055 meter, and for the watts we take the 90 watts, and we use the formula of K, that is WL over area times with T1 minus T2, and we calculate the area, that is area A equal to pi r square. Then we insert the diameter, we divide by 2 because the diameter to change to radius divide by 2, and when we get the area value, we insert the area into the formula, and then we calculate. And for the brass thermal conductivity are 122.1896 watts meter K. And for its typical value is 123 watts, and I did almost the same because there must be a error when we taking the data. And we proceed to the stainless copper. On the stainless copper, we use the same procedure for the brass, and we use same procedure for calculation on the brass. As you can see here, for the data, for the final answer of thermal conductivity K is 109.3183 watts, and the typical value for the stainless copper are 386 kilowatts. This may be the equipment error or human error during the experiment that may have the effect to the data. And we proceed for the next slide. It is stainless steel. On stainless steel, we use the same formula and same calculation for the brass and stainless copper, and we use the formula. We will get the K for the stainless steel are 102.62 watts, and for its typical value are 16. This is also the same. Maybe the data are incorrect because the equipment a problem, or the equipment problem, or the user incorrectly taking the data. Okay, and we proceed to the next slide. For this discussion number 3, the question is, what can you observe from the gradient of the chart for each heater power setting? And for our answer, from the data, on the gradient of this chart has a different type of material and has a different temperature when reached interval of 5 minutes of data taken. And for the second point, the longer the length of the distance, the lower the temperature are collected. This happens because the wider the area of surface, the longer the temperature to spread. And for the third point, from the gradient, we are able to observe that from each material has almost the same thermal conductivity. The longer the distance, the lower the temperature. For other material, there is brass, stainless steel, and stainless copper. And for the next slide, for the discussion on number 4, For the question, add a best fit line throughout the result to find the best overall thermal gradient. From the overall result, find the thermal resistance R value for the whole bar. Then use the thermal resistance in series method to find the R, and then find the K value for the middle section. And by using the K value you find from the first procedure for the brush section, this side of the middle. And proceed to the next slide. Then this is the graph for our gradient for the brush. As you can see, the data almost the same with the gradient line. And then we proceed to the next slide. For the calculation of the data, as you can see here, for our T1 of the brush is 343.8, and the for T7 is 306.6, and for our K of the brush is 122.1896, and for the area we take the 2.376 times by 10, and then we proceed for the calculation. For the R brush, the formula are we using L over Ka, and we insert the data, and the final result is we get 0.068, and then we proceed for the R total. For the R total, the formula we using are T1 minus T7 over W, and we insert the data. And for the W, we will be using the 90 watts because that the power setting our team are using. And then for the result of our total is 0.4133. Then we proceed to the R mid. For the R mid, the formula we using are R total minus 2 brush. And we insert the data. There is 0.4133 minus 2 times by 0.068, and the final result or the final calculation we get for the R mid are 0.2773. Now we proceed for the K mid. For the last calculation on the K mid, the formula we using for the K mid are L mid over R mid times by area, and we insert the data. Then for the final answer for the K mid, that our team get 30.35 watts over meter K. That's for the calculation. We proceed for the conclusion. We proceed for the conclusion. For the conclusion, during this lab, we are able to learn how the linear conduction operates and how to operate the linear conduction tool or machine, and able to collect the data effectively. And this lab also teach us how different material has a different heat conduction for the heat to conduct. This lab also help us to learn the thermal phase help the linear conduction to operate efficiently with the heat to conduct to the each material I use. And for the last point of the conclusion, from the data from this lab, we also able to plot K, the thermal conductivity from the data collected, and we are able to use formula for each material for experiment.